Welcome to module 2 of chapter 9. In this module we are going to consider another matrix representation of the graph called incident matrix of the graph. The size of incident matrix is mod V cross mod E or n cross m, where n is the number of vertices and m is the number of edges. There are two types of incident matrices. For a given graph we will give some orientation to the edges. Then the incident matrix of resulting digraph contains entries -1, 0, 1. The incident matrix with entries -1, 0, 1 is denoted by Q of x. The 0, 1 incident matrix is denoted by I of x. In module 2 of chapter 9, we are going to discuss incident matrix of a graph. The learning objectives of this module are: incident matrix of a graph with entries 1, -1, 0, 0, 1 incident matrix of a graph. Let x be a graph with vertex set V of x equal to 1, 2, 3 and so on n, and edge set E of x equal to E1, E2 and so on Em. Suppose each edge of x is assigned an orientation which is arbitrary but fixed. It is called the vertex edge orientation. The incident matrix of x denoted by Q of x. If x is clear from the context, then we simply denote it as Q, is the n by m matrix, where it is easy to see that n is the number of vertices in the graph and m is the number of edges in the graph. Q of x is defined as follows: the rows and columns of Q of x are indexed by vertices of x and edges of x respectively, and the ijth entry of Q of x is 0 if vertex I and edge ej are not incident. As we know that if we take a vertex and edge, then we will say that incident, whereas if I take two vertices, then we will say that they are adjacent. So, the vertex I is not incident with edge ej. In that case, the ijth entry of Qx is 0. The ijth entry of Qx is 1 if ej originates at I. It is because we are giving some direction to the edges. So, for each edge what happens? It begins at a vertex I and terminates at other vertex. So, if it is originates at I, then we will say that in that case the ijth entry of Q of x is 1, and it is -1 if ej terminates at vertex I. So, that is the reason the entries of Q of x are either -1 or 0 or 1. For example, consider the following graph. This graph contains 4 vertices 1, 2, 3, 4, and it has 5 edges E1, E2, E3, E4, E5. So, the incident matrix size is going to be 4 by 5. So, now we will assign some orientation to its edges. This orientation is arbitrary. We can give whatever the way we like. For example, in this case we given that the edge E1 is a directed edge from 1 to 2. That means it originates at vertex 1 and it terminates at vertex 2. The edge E2 originates at vertex 3 and terminates at vertex 1 and so on. So, consequently the incident matrix of this graph, directed graph, is going to be given like this. That is, the first row now, that is related to the first vertex. If you see that there are 3 edges incident at vertex 1, the edge E2 terminates at vertex 1, whereas edge E1 and edge E3 are originates at vertex 1. So, that is why we put 1 for edge E1, -1 for edge E2, and again 1 for edge E3. For edge E4 and edge E5 it is 0. So, here the rows are indexed by the vertices and columns are indexed by the edges. So, similarly, if you look at the second vertex or second row, so the degree of vertex 2 is 2. So, but both the edges are terminating at vertex 2, that is why both the values are -1. So, one is for the edge E1, other is for the edge E4. Similarly, we have other rows, that is row 3 as well as row 4. Now, if you look at the matrix carefully, of course, it is not a square matrix because the number of edges and number of vertices are not same for this graph, but we can see some other observation, that is, if you look at each column contains two non-zero entries, 1 and -1. So, if you add all the rows, we are going to get 0. So, that is why it is easy to see that the rows are linearly dependent. So, now we will see few properties of this -1, 0, 1 incident matrix. First condition is that, first property is that rank of q of x is less than or equal to n minus 1. In that example we already discussed, but again we will state, for any graph x, each edge originates at a vertex and terminates at another vertex, though sum of the entries and in each column of q of x is 0, hence the rows of q of x are linearly independent. We will now proceed to determine the rank of q of x. If x is a connected graph and n vertices, then rank of q of x is equal to n minus 1. That means, if the graph is connected, then exactly the rank of q of x equal to n minus 1. Otherwise, we already observed that the rank is clearly less than n, so it is less than or equal to n minus 1, but if the graph is connected, then rank equal to n minus 1. Now, we will see the proof. Suppose x is a vector in the left null space of q, that is equal to q of x, that is x transpose into q equal to 0 transpose, where 0 is the 0 vector with all entries as 0. Then it is easy to see that xi minus xj is equal to 0 whenever the vertex I is adjacent to vertex j. It is because we have in each column we have two non-zero entries, one is 1, other is -1, that is why we have this. It follows that xi equal to xj whenever there is a path from I to j. Consequently, all the components of x are equal. This is a nice property. Thus, the left null space of q is at most one dimensional, and therefore, the rank of q is at least n minus 1. Also, as observed earlier, the rows of q are linearly dependent, and therefore, the rank of q is less than or equal to n minus 1. Hence, rank of q equal to exactly n minus 1. Another theorem, if x is a graph on n vertices and k connected components, then rank of q of x is equal to n minus k. Let x1, x2 and so on xk be the connected components of graph x. Then after relabeling of rows and columns, if necessary, we have q of x equal to q of x1, q of x2 and so on q of xq, and the remaining 0. The q of x1, q of x2 is on the diagonals. So, it is a block diagonal matrix. Since xi is connected, the rank of q of xi is ni minus 1, where ni is the number of vertices in the component xi. So, for I is equal to 1, 2, 3 and so on k. Hence, it follows that rank of qx is equal to rank of qx1 plus rank of qx2 and so on plus rank of qxk. But rank of qx1 is n1 minus 1, rank of qx2 is n2 minus 1 and so on, rank of qxk is nk minus 1. So, it is equal to n minus k, hence the result. Now, we will see another important result on q of x. This is about the column space. Let X be a connected graph on n vertices, then the column space of Q of X consists of all vectors X belongs to R power n, that is n cross 1 matrix with real entries such that summation xi is equal to 0. That means sum of all the entries xi is equal to 0. Proof, let U be the column space of Q of X. Let W equal to X belongs to R power n such that summation xi is equal to 0. Then dimension of W is n minus 1. By definition, each column of Q of X is in W. Hence, U is contained in W. But from theorem 1 or previous theorem, we saw that rank of Q of X is dimension of the column space of Q of X, that is equal to n minus 1, as X is a connected graph on n vertices. So, U is contained in W and rank of W is n minus 1, dimension of W is n minus 1. So, U equal to W. So, we proved this result. Another theorem, let X be a graph on n vertices, the columns J1, J2 and so on Jk of Q of X are linearly independent if and only if corresponding edges of X include an acyclic graph. So, it is an important result. Here what we are saying is the columns J1, J2 and so on Jk of Q of X are linearly independent if and only if corresponding edges of X induce an acyclic graph. Acyclic graph means without cycles. Proof, consider the edges J1, J2 and so on Jk, and suppose there is a cycle in the corresponding induced subgraph. Without loss of generality, suppose the columns J1, J2 and so on Jp form a cycle. After relabeling the vertices, if necessary, we see that the submatrix of Q of X formed by columns of J1, J2 and so on Jp is of the form B0, where B is a P by P incident matrix of the cycle formed by the edges J1, J2 and so on Jp. Note that B is a square matrix with column sums to 0. Thus, B is singular, hence the columns J1, J2 and so on Jp are linearly dependent. This proves only if part of the lemma. This is a we proved by contradiction. So, J1, J2 and so on Jk are linearly independent, the columns. Conversely, suppose that the edges J1, J2 and so on Jk induce an acyclic graph, that is a forest. If the forest has q components, then clearly k is equal to n minus q, which is by previous theorem, that is the rank of a q related to number of connected components is the rank of submatrix formed by the columns J1, J2 and so on Jk. Therefore, columns J1, J2 and so on Jk are linearly independent, hence the result. Now, we are going to define a totally unimodular matrices. A matrix is said to be totally unimodular if the determinant of any square submatrix is either 0 or plus or minus 1. That means, we will consider all square submatrices. For each square submatrix, the determinant is either 0 or plus 1 or minus 1. Not only for the entire matrix, every submatrix determinant is either 0 or plus 1 or minus 1, then we will call that matrix as a totally unimodular matrix. Let X be a graph with incident matrix Q of X, then Q of X is totally unimodular. So, the incident matrix with minus 1, 0, 1 are good examples for totally unimodular matrices. Proof: consider the statement that any k cross k submatrix of Q of x has determinant 0 or plus 1 or minus 1. That is, we are considering this statement. So, we are going to prove by induction on k. We will prove the statement by induction on k. Clearly, that statement is true for k equal to 1. That means, if the matrix contains only one entry, that entry is either 0 or plus 1 or minus 1. Clearly, its determinant is 0 or plus 1 or minus 1. So, the result is true for k equal to 1. Assume the statement is be true for k minus 1 and consider k cross k submatrix B of Q of x. Now, we have to show that the determinant of B is also 0 or plus 1 or minus 1. If each column of B has a 1 and a minus 1, then determinant of B equal to 0. Also, if B has a 0 column, then also determinant of B equal to 0. So, suppose that B has a column with exactly one non-zero entry, which must be plus or minus 1. Expand the determinant of B along that column and use induction assumption to conclude that determinant of B must be 0 or plus or minus 1. So, with this we proved this result, that is, every incident matrix with entries minus 1, 0, 1 is a totally unimodular. Now, we will prove another result. Let X be a tree on n vertices, then any submatrix Q of x of order n minus 1 is non-singular. Let C be a submatrix of Q of x formed by the rows 1, 2, 3 and so on n minus 1, and D be the submatrix of Q of x formed by the rows 1, 2, 3 and so on n minus 2 comma n. Consequently, the first n minus 2 rows of C and D are same, and the determinant of C will not be affected if we replace its last row by adding all its rows, but then the last row becomes the negative of the last row of D. Consequently, the determinant of C is equal to minus determinant of D. Continuing in this way, we can show that if determinant of C equal to 0, then every n minus 1 cross n minus 1 submatrix of Q of x is singular. So, but by theorem 2, that is, we proved that if x is a connected graph, then the rank of Q of x is n minus 1. So, if every n minus 1 cross n minus 1 submatrix of Q of x is singular, that is determinant is 0, then clearly the rank of Q of x has to be less than n minus 1, which is a contradiction for the theorem. We proved that if x is a connected graph, then rank of Q of x is n minus 1. Hence, every minor of Q of x of size n minus 1 is non-singular. Hence, we proved this theorem. Till now, we discussed various results on minus 1, 0, 1 incident matrix Q of x. We showed that Q of x is totally unimodular matrix. The rank of Q of x provides information about number of connected components of the graph x. Now, we will see results on 0, 1 incident matrix. Now, we will see another incident matrix. It is called 0, 1 incident matrix of the graph. Let X be a graph. The incident matrix is a 0, 1 matrix denoted by I of x, in which rows are indexed by the vertices and columns are indexed by edges, with I of x e is equal to 1 if the vertex x is incident with the edge e, 0 otherwise. Now, we will see an example of a 0, 1 incident matrix. The incident matrix is the following graph. This graph we already defined earlier. So, this graph contains 4 vertices and 5 edges. The incident matrix is given as I of x equal to 1, 1, 1, 0, 0 and like that. So, if you look at the first row, it has 2 consecutive ones followed by 2 consecutive zeros. It is because the vertex 1 is incident with the edges E1, E2 and E3. So, we already noticed that we will index the rows with the vertices 1, 2, 3, 4 and we will index the edges, we will index the columns with edges E1, E2, E3, E4, E5. So, E1, E2, E3 incident with vertex 1. So, we have 3 consecutive ones followed by 2 consecutive zeros. Similarly, row 2 is related to vertex 2. So, the vertex 2 is incident with edge E1 as well as edge E4. So, here we have 1 0 0 1 0. So, if you look at this matrix carefully, each column contains 2 ones and the number of ones in each row gives the degree of the vertex, etc. So, now we will see properties of this incident matrix. So, another example is that if x equal to C3 union K2, that is it is a union of cyclic graph C3 or complete graph K3 and complete graph K2. So, here first 3 rows are indexed by vertices of C3 and the last 2 rows are indexed by vertices of K2. So, you can see that the last 2 rows are identical because they are related to vertices in K2, they both are incident with only one edge, the edge corresponding to K2. So, this is another example to understand what is 0 1 incident matrix. Now, we look at few properties of 0 1 incident matrix. Since every edge is incident on exactly 2 vertices, each column of I of x has exactly 2 ones. The number of ones in each row equals the degree of corresponding vertex. The row with all zeros represents an isolated vertex. Parallel edges in the graph produce identical columns in the incident matrix. Parallel edges means multiple edges, means if 2 vertices will have more than one edge, then they are called parallel edges. If a graph x is disconnected and consists of 2 components x1 and x2, the incident matrix I of x can be written in block diagonal form as I of x equal to I of x1 0 0 I of x2, where I of x1 and I of x2 are incident matrix of components x1 x2 respectively. Permutation of any 2 rows or columns in the incident matrix simply corresponding to relabeling the vertices and edges of the same graph. Now, we will prove an important result on incident matrix 0 1 incident matrix of a graph x. If x is a connected graph on n vertices, then rank of I of x is equal to n minus 1 if x is bipartite, n otherwise. So, in other words, rank of I of x is greater than or equal to n minus 1. It is little different from in q of x case. In q of x case, rank of q of x is exactly n minus 1. So, here it is greater than or equal to n minus 1 and it is n minus 1 only if x is bipartite. If let x be a graph, let I of x be its incident matrix. Now, each row in I of x has exactly 2 non-zero entries. So, for any x in the left null space of I of x, we have xi plus xj is equal to 0 whenever the vertices I and j are adjacent. As x is connected, so mod of xi is equal to alpha for all I is equal to 1, 2, 3 and so on n. It is because since it is connected, there is we have a path from any vertex to any other vertex. So, from the equation xi plus xj equal to 0 whenever vertices I and j are adjacent, we have that xi equal to minus of xj. So, consequently modulus of all xi are equal to alpha. Now, if x has a odd cycle consisting of vertices I1, I2 and so on I 2k plus 1, then from above we see that xi1 is equal to xi3 is equal to and so on, xi2k plus 1 is equal to xi2 and so on, xi2k is equal to 0. So, because of hard cycle, last vertex and first vertex need to have same value. So, it forces all the values as need to be equal, but we have that xi plus xj is equal to 0. So, because of that all are going to be 0. Hence, in this case rank of Ix equal to 1. It is important to note that in this case number of edges is greater than or equal to n as x has a cycle. If x has no cycle of odd length, then x is bipartite. Let the bipartition of the vertices be A and B. Then from above we see that the vector x having 1 corresponding to elements of A and -1 corresponding to elements of B is an element in the left null space of I of x. Hence, in this case rank of I of x is less than or equal to n minus 1. Now, we are going to show that rank of I of x is greater than or equal to n minus 1. Also, if we orient the edges of x, so that every edge terminates at an element of B, then corresponding -1 0 1 incident matrix Q has rank n minus 1. Moreover, observe that the matrix Q is obtained from I of x by multiplying the rows corresponding to elements in B by -1. Now, we choose the columns I1, I2 and so on in minus 1 of Q, which corresponds to spanning tree of x. Then by previous result, the rows of corresponding submatrix of Q are linearly independent. Also, the columns of I of x and Q coincide up to the sign corresponding to rows of I of x are also linearly independent. Thus, rank of I of x is greater than or equal to n minus 1. So, if we note that rank of I of x is less than or equal to n minus 1, now the rank of I of x is greater than or equal to n minus 1. Hence, we have rank of I of x equal to n minus 1 whenever x is connected and bipartite graph. Now, we will see few exercises. We are not giving the proofs for this, but they are easy to show. Let Cn be a cycle on n vertices where n is greater than or equal to 3, then determinant of incident matrix of Cn is equal to 0 if n is even, 2 if n is odd. Another important result is, let Q be a bipartite graph, then incident matrix I of x is totally unimodular. So, earlier we showed that Q of x is always totally unimodular, but I of x is also totally unimodular whenever x is a bipartite graph. Now, let x be a graph on n vertices and m edges. Let us assume m equal to I of x, where I of x is the incident matrix with entries 0 and 1. Then m transpose into m is equal to AL plus 2 IM, where IM is the identity matrix of size m by m, where AL is the adjacency matrix of a line graph of x and IM is the identity matrix of order m. If x is a k regular graph, then MM transpose is equal to A plus k into IN, where A is the adjacency matrix of the graph and IN is the identity matrix of order n. The proof for the part 1, the ijth entry of M transpose into M is a dot product of ith and jth column of M. That is easy to see. M transpose into M means simply the ijth entry becomes is the dot product of ith and jth column of M. But each column of M contains exactly 2 ones. Because of this, we will get M transpose into M is equal to 2 if I is equal to j, is 1 if I not equal to j and I and j are adjacent, is equal to 0 if I not equal to j and edges I and j are not adjacent. Proof of part 2 also done in the similar fashion. Just we need to consider m into m transpose, we will get the same part. Now, bounds on eigenvalues of a line graph of a graph, that is, if let x be a graph and lambda be an eigenvalue of the line graph of x, then lambda is greater than or equal to -2. Let lambda be an eigenvalue of line graph of x, then by previous result AL is equal to, that is the adjacency matrix of the line graph is equal to m transpose into m minus 2 times I m. We already showed that m transpose into m is equal to AL plus 2 into I m, because that we will get this. So, if Z is an eigenvector of AL corresponding to eigenvalue lambda, then Z transpose into lambda Z is equal to Z transpose AL Z. It is because Z is an eigenvector of AL corresponding to eigenvalue lambda. So, which is equal to Z transpose into AL value, now we are substituting, that is m transpose into m minus 2 I m. If you substitute, then we will get. So, this is Z transpose m transpose can be written as mz whole transpose. So, mz whole transpose into mz minus 2 times Z transpose into Z into I m. So, we will get norm of mz whole square minus 2 times norm of z square. So, or equivalently lambda minus 2 times norm of z square is equal to norm of mz whole square. Hence, lambda is greater than or equal to -2. If x is a connected graph, we showed that the rank of I of x is greater than or equal to n minus 1. Further, if x is bipartite, then I of x is totally unimodular matrix. Using 0 1 incident matrix, we showed that the eigenvalues of line graph of a graph are greater than or equal to -2. With this, we end this module.